All right, AP students, welcome to your rate law walkthrough. So we're just going to go ahead and get right into it. So for our conceptual, we're going to practice determining the reactant order for individual reactants in a chemical reaction. So calculate the rate law using the data below. So we're given a bunch of experimental data, which, by the way, rate law can only actually be determined through experiment. And what we're given is the initial concentration and therefore the initial changes in concentration. Recall that when we calculate rate law from experimentation, in order to get the most accurate relationship between the concentration and the rate of the reaction, we take our initial values so that we are not having to consider the natural slowing that occurs when you're just simply running out of particles to react. All right. And we're given a balanced chemical equation with the synthesis of NO2, nitrogen dioxide. And what we are asked is A, what is the order for NO? So what you have to realize is when we look at these reactants and we're trying to determine reactant order, we want to look at trials where the rate of the other or the concentration of the other reactant is not being affected, but the concentration of our reactant that we're observing is changing. So what we would find is that I am going to select for analyzing NO, I am going to select trial. Let's see. We have consistency here. I'm going to select trial 1 and trial 3 to examine. And what we would find is that for our rate law equation, it is rate equals some constant K times the concentration of A raised to a power times the concentration of B raised to another power, okay, raised to the reactant order. So when I look at this question, I would say, well, my rate for trial 3 was 2x, okay, and my rate for trial, okay, 1 is going to be x. So I'm going to try to establish a relationship between the change of each experiment. And I know that's also going to be equal to the K1 times the concentration of our given compound times the raised to a certain power times the concentration of our other reactant raised to a certain power. All right, so I'm going to set that equal to, well, what is rate 3's portion of this? What does rate 3's portion of that look like? And I'd say, well, 2x, the concentration of NO is 0.0020 raised to some power times the concentration of the other reactant, which is 0.0010, okay, raised to some power times K of 1, right, times some constant K, sorry, K of 3, whoops, K of 3, experiment 3. And then I'm going to say that's going to be compared to experiment 1 concentrations, which is going to be K1 times 0.0010 raised to some power x times the other concentration of the other species, which is 0.0010 raised to some power y. And what you'll see is that the K's basically cancel out because you're working with the same reaction. So the overall rate of reaction, given this particular stoichiometric ratio between the reactants, is not going to be different. So we can almost cancel out the K's. And we can cancel out this whole section of the concentration of my other element, O2, and its exponent because it'll naturally cancel itself out. So what we're left then is we're left with 2x divided by x is equal to 0.0020 raised to the power of x divided by 0.0010 raised to the power of x, okay? And what that becomes is, we'll simplify it, and it becomes 2 okay? Because then the x's cancel out. 2 equals 2 raised to the power of x. And that means that our x is equal to 1, representing a first order relationship, reactant order relationship between our concentration of NO reactant species and our rate. So that means when our NO species doubles in concentration, so does our rate. Okay, so let's move on to the next compound. All right, so for the O2 species, we're going to do the same process. And this time we're going to pick trials where we see a change in O2, but no change in the concentration of NO. So I'm going to pick trial 1 and trial 2. Okay, trial 1 and trial 2. And I'm going to set up similarly. Okay, I'm going to do rate of 2 all over rate of 1 is equal to 2x over x, which is going to be equal to the concentration of O2, which is in trial 2, 0.0020 raised to the power of y times the concentration of NO raised to the power of x, which again, you're going to quickly notice is going to cancel out, times the rate, experiment 1 concentration of O2 was 0.0010 raised to the y times the concentration of NO, which again, we're going to see gets canceled out. Okay, and we'll see that, do a different color. We'll see that these get canceled out because it's unchanging, so it acts like a constant. The K is going to remain the same, so it's going to naturally cancel out because we're talking about the same reaction. And we would find that we get a similar simplification down to 2 equals 2 raised to the power of y, telling us that the reactant order with regards to the reactant species of pure diatomic oxygen is also going to be first order. So if we double O2 concentration, keeping NO concentration constant, we would see a double in our rate of reaction. So the question then is, what is the rate constant for this reaction? So what we do is we now set up our final rate law now that we have our respective reactant orders, and we say that that the rate of reaction is equal to K times the concentration of NO raised to the power of 1 times the concentration of O2 raised to the power of 1. And then what we would do is we'd rearrange to solve for K. So we would say then that K is equal to the rate all over concentration of NO times concentration of O2. And we would get then this relationship for solving for K. And then we would simply, all right, plug in a given trial's data into this formula and solve. So what we have here is 1, you should note that the initial rate of formation is going to be in the units of meters per, meters, good God, molarity per second. Okay, that's kind of how we track the time it takes, is how many molar value of a product is being made in a certain amount of time, seconds. So what we would get then is, I'm going to choose, let's just go different. I'll choose trial 4 data just for the heckaroonies of it. Okay. Actually, that's way bigger numbers. I'm going to choose trial 1 data because I just don't want to deal with big numbers. And given trial 1 data, okay, I'm going to say that K is equal to the rate of trial 1, X meters per second, all over the concentration of NO in trial 1, which is 0.0010 times the concentration of 0.0010. And that's going to equal x, okay, all over 1 times 10 to the negative 6. And this would be molarities squared, because this is concentration. And this would be molarity per second, simplifying down to x over 1 times 10 to the negative 6, molarity negative 1 seconds negative 1. And that would be your final answer. Okay, for the value of K, which is our rate constant, which we use to compare. So what then is the rate law for this reaction? Well, the rate law is now we go in and we plug our known value for K into it, and we say that the rate law is equal to, what did we discover K to be? X over 1 times 10 to the negative 6, molarities to the negative 1, seconds to the negative 1. Okay, that's all K times NO concentration raised to the power of 1 and O2 concentration raised to the power of 1. And there you have it. So that's kind of the breakdown of how we would use experimental data to determine the rate law, given initial concentration and initial rate of formation. Okay, guys, good work. Let's move on to the next one. I have only one more conceptual, and then we'll head into a long FRQ. So for question number 11, we are being asked to consider the following equation that has been balanced for us, and we are given its rate law. So we are asked then, what is the reactant order for H2 with respect to H2? And we would say first order, because we assume that if there is not a number written, the exponent is 1. If the exponent was 0, it would make the entire value 1, which is a constant. So we know that can't be true. So it's definitely first order. What is the reaction order for the reactant I2? It is also first order. Okay. And again, you don't see a written exponent, which means that we can assume it's a 1 value. And then what would the units be for this rate constant for the equation? What we would find is our previous problem kind of gave this idea for a situation where you have two reactants, both being first order. We would see that our rate constant value units would be m to the negative 1, molarities to the negative 1, and seconds to the negative 1. All right, so our previous problem kind of helps us with this. Honestly, this might be just kind of an area of memorization or letting the problem speak for itself in regards to determining the units for K. And I probably will have mentioned that in class. I don't know why I keep on passing by this, but that's just kind of my tip. So that's kind of just a short overview of how to read a rate law expression. And let's go ahead and hop to the long FRQ. I believe we're going to do question number 6 or 5. Give me a second to find. What did I mark? Oh boy. Question number 5, long FRQ. All right. So for this long FRQ, this is, again, of course, a reminder that FRQ problems are going to begin stacking more and more of your previous units involved in your FRQ portion, like part A, part B. So don't forget to stay up to date on all the other material. Although granted, you should naturally be quite up to date, because I don't know how you do these problems without knowing previous material. And what we have here is an unknown gas D reacts with fluorine gas to form the compound DF4 as represented by the following equation. A series of experimental trials, remember, because rate law can technically only truly be determined through experiment. We can create a bunch of theory and patterns, but in the end, true rate law is only determined through experimentation. Was performed at 600 degrees Celsius to determine the rate law expression for the reaction. Data is given below. And again, it's all initial. So, and notice actually we're in pressure here because we're working with gases. And don't forget that pressure is often an equivalent way for determining concentration of gases. So just notice that slight change, but the way that we treat it or in the way that we do our problem is exactly the same. All right. And a student claims that the reaction is first order with respect to F2. Do you agree or disagree? So remember that first order requires that if you increase your reactant concentration, right, by double, then you should see that your rate also doubles, right? It's a 1-to-1 ratio of change. So when we look at the trials, what we see is when we look at F2, we want to find the trial where D doesn't change in pressure or concentration. And so it would be trial 1 and trial 3 that we would compare. And what we see is between trial 1 and trial 3 for analyzing F2 impact on rate of reaction, we see that the reaction quadruples, okay? But the concentration or the pressure doubles for F2. So what we actually see is we would disagree because when analyzing trial 3 and trial 1 data, the doubling of F2 pressure results in a quadruple increase in rate, indicating all right, a second order relationship with F2, with respect to F2. A second order, all right, relationship with respect to F2. Okay, so what is the initial rate of disappearance of F2 in trial 3? Justify your answer. So what we see is that we have an initial rate of appearance of DF4 at 20.0 times 10 to the 3. Now, when we look at our balanced equation, so we know that 20.0 times 10 to the negative 3 is the appearance of DF4. And we know from our balanced chemical equation that for every 1 DF4 made, we use up or disappear, right, 2 F2s, okay? And so, and I totally forgot my units. Oh my goodness gracious. How could I do that? You guys like don't care, but I do because it helps. So, torr per minute. Okay, so I know then that for every 2 F2 torr, because it looks like we're measuring pressure in torr here, which is unusual, we have a 1 torr of DF4 being produced for every 2 torr of F2 being consumed, or concentration amount, right? This is all indicative of concentration. And that means that given our stoichiometric relationship, that F2 would disappear at a rate of 4.0 times 10 to the negative 2 torr per minute. F2 disappears. Okay. C, a student claims that if element D is in group 18, then the molecular geometry of DF4 is square planar. Okay. Do you agree or disagree with the student? So here's the thing to remember is if element D is in group 18, we know then that element D would have 8 valence electrons. We know that F is going to have 7 valence electrons, giving us a total of 28. So we know that our total valence electron count would be 28 plus 8, which is equal to 36. So let's graph out this. Let's put D in the middle. F, 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 and F. We've used up 8 right there. So we have 28 left. We will distribute 6 to every fluorine. Okay. Okay, so that means I would use up 24, giving me 4 left. I'd have to put those 2 extra on the center. And I guess I'm assuming this is a noble gas element that can handle more than an octet, an expanded octet. And what I would see is that this would give me a structure of an electron domains of 6 electron domains, which would give me an electron geometry of octahedral. But with the 2 lone pairs, the molecular geometry would indeed only account for the shape developed by the 4 bonded electron domains. So we would indeed get square planar. So our overall, we would say, yes, we would agree because DF4 would have 36 valence electrons that would result in 4 bonds and 2 lone pairs around central, which is consistent with square planar. Okay. Okay, part D/E has another little mini prompt. The particulate model shown below represents the moles of particles present in the container after D and F2 are reacted in different experiment. Assume that each particle in the diagram represents 1 mole of the respective substance. Note the box corresponding to before reaction is intentionally left blank. Okay, I love how they have to tell us that. So what we see here is if the total pressure at the end of the reaction is 12 atm, what is the partial pressure of D? Okay, so this is Dalton's law of partial pressure. And so what we would say is we know that the total pressure is 12. And the question is, what is the pressure contributed by D? So if we look at this ratio here, we see for every mole of gas, we have how many moles of gas? Let's count. We have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. Okay. I miscounted. Hold on. I'm losing track. The dots were not big enough for me to track. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So here I have a representation of 15 moles of gas, right? Because it assumed that each particle in the diagram represents 1 mole, okay, of the respective substance. So that's my total. P total is equal to 15 moles of gas. Okay, and what I see is that my D molecule is the plane circle. So it's 1, 2, 3. So as far as the pressure of D, it is 3 moles of gas. So what I would do is I would multiply by my molar ratio, or what we might call our mole fraction, right? Times XA, which is going to be equal to 12 atm times 3 moles of D all over 15 moles of gas, which is going to give me a value of 2.4 atm from D gas. Okay. All right, so now looking at the next question or part, we are told that assuming that only D and F2 are present in the container before the reaction, determine the number of moles of D and F2 that were present in the initial reaction mixture. Okay, so we'll determine the number of moles of D and F2 that were present in the initial reaction mixture. So we know that we created DF4. We created how many molecules of DF4? Let's see, let's highlight those. We created 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules of DF4, or 10 moles of DF4 were created according to this particulate diagram. And so to have 10 moles of DF4, that means according to our stoichiometric ratio, we'd have to have 10 moles of D and 2 times 10 of F2. So that means that we'd have to create 10 moles of DF4, 10 moles of D, and 20 moles of F2. And so what we see then is we know we have 10 and 20, but then we look at our remaining amount and we see that after reaction, we also have excess of each one. So we would add to the excess. We know that we already have from our previous problem, we've identified that there are 3 extra moles of D, and that F2 wise, we have 1, 2 extra moles of F2. So giving us a total of before reaction, 13 moles of D and 22 moles of F2. We're going to skip over the next part, F and G, and we are going to move on because it revolves a little bit future material. We're going to move on to the last part. While investigating the properties of other diatomic molecules, the student finds the diagram below, which shows the potential energy of 2 iodine atoms versus the distance between their nuclei. Okay, this is a throwback to Unit 1-2. The students also find that the I don't know what happened to the space right there, bond energy is slightly less than F2 bond energy. The student incorrectly sketches. Okay, so we already know this is incorrect. The potential energy curve for the 2 fluorine atoms shown below in the dotted line. Okay, and then explain the error that occurred. So first things first, we got to understand that F2 is going to be smaller in size than I2. Okay, because F is the most Coulombic attraction experiencing atom, which means it has the greatest pull between its nucleus or greatest effective nuclear charge occurring and its electrons, and therefore it's going to be tiny. So automatically when we see this, okay, we should see that the bond, even though they're both single bonds, this bond will be shorter in length, relatively speaking, due to the smaller size, the smaller internuclei distance. And therefore, it will be a slightly stronger bond. And therefore, it'll be slightly more stable, right? So what we would say is that the error the student made is the F2 curve should be lower than the I2 curve to represent, okay, the more stable and stronger / shorter bond, okay, between F and F, okay? So there we go. That is pretty much all of long FRQ 5, except for those 2 sub problems right there that aren't too long at all, but we just haven't learned that material quite yet. And remember, it takes about 23 minutes and is a lot about 10 points on the AP exam. And so hopefully this is a nice overview. We're going to start getting into our calculus derived integrated rate law tomorrow. And best of luck, everyone. Good job.